Hello everyone. Today I'm honored to share my technical practice in stroke risk prediction model development. This project addresses the common problem of category imbalance and complex feature in medical data, and finally achieves efficient and accurate risk warming through a systematic machine learning progress. First, I used light GBM as a classification model, which is an efficient gradient boosting framework suitable for handling unbalanced data and high-dimensional features. The SMOTE method is used in the code to solve the category imbalance problem to balance the positive and negative sample one, which is helpful to improve the recognition rate of few classes. Then virtual energy was performed on the data, including binning and creating new features such as age groups, BMI categories, and blood glucose level categories, which can help the model capture nonlinear relationships. For model training, I used early stopping to prevent overfitting, which was achieved by monitoring the AUC metrics of the validation set, which is more in line with the need of medical scenarios. In addition, appropriate appropriate evaluation metrics were selected, such as AUC recall and F1 score, which are commonly used when dealing with imbalanced data. Especially, recall is very important in the medical field because the cost of missed diagnosis is high. Regarding performance optimization, I set large N estimator in conjunction with the early stop method to automatically determine the optimal number of iterations, which reduces unnecessary computations while ensuring that the model doesn't stop prematurely. For parameters, subsample and co-sample by tree were used to subsample features and data to increase the generalization ability of the model. The regularization parameters reg alpha and reg lambda are also set to help prevent overfitting. In this part of the code, we can see that age, blood glucose level, and BMI are firmly in the top three of feature importance, which is highly consistent with the medical consensus. In terms of evaluating and improving the fit, I divided the data into training set and validation sets using stratified sampling to ensure a consistent data distribution. The performance of the validation set was monitored through the early stop method, which synchronized the tracking of AUC and the cross entropy loss, and terminated the training after 50 rounds of no improvements, stopping the training in time to avoid overfitting. Visualization of feature importance help to identify key features that may be further subjected to feature selection or energy. In addition, the optimal number of iterations is used when retraining the model to ensure that the model is at the best for prediction. By analyzing the training and validation curves, I found that the validation set boasts the level of after more than 100 rounds of the iterations, proving the efficiency of early stop strategy. In the future, an interpretability model can be developed to introduce SHAP values to parse individual risk or adjust dynamic threshold to flexibility set early warning lines based on medical resources. To summarize, optimization measures including deal with data imbalance, feature energy, model selection, and parameter tuning, early stopping method, and the use of appropriate evaluation metrics. Evaluation method, on the other hand, including monitoring of the validated set, early stopping, feature importance analysis, and retraining of the final model. That's all. Thank you for listening.